Hi everyone, this is Prof. K speaking, and today we're going to talk a little bit about catalysts, which are another type of chemical species or substance sometimes, or there's lots of different sort of types of catalysts. We're going to talk about what role they play in reaction mechanisms and how they can affect activation energies. So let me get the slides moving. Catalysts and our learning objective is to explain the function of catalysts in terms of reaction mechanisms and potential energy diagrams. So if we go back to a mechanistic expression, like the ones we talked about in the previous videos, we can have sort of different types of steps and different reactions. And so we talked about intermediates, which are produced during one step of the reaction and then get consumed in a later step. A catalyst is a substance that can increase the reaction rate but isn't consumed by the reaction, or by the end of the mechanism is restored. And so I'll show you examples of something not being consumed versus something that's consumed and then restored. But ultimately, a catalyst in this mechanism will look like something that goes into the start of our mechanism. It speeds up that particular step of the reaction and it comes back out at the end. So this is different than an intermediate because it doesn't appear and then disappear. This appears and by the end has to reappear. And so that's what sort of a catalyst does. And if you've heard about a catalyst before, maybe you've heard that catalysts reduce activation energy. But if not, I'm going to explain. So catalysts can affect activation energy by changing the energies of the transition state or by the mechanism even of a reaction. And so both of these reaction coordinates are possible effects of maybe different catalysts. And so if purple represents the uncatalyzed system, it has a relatively high activation energy. And when you add in your catalyst, you recover this orange energy surface or a lower activation energy. And so it lowers this activation energy. It's helping whatever transition state is happening be more stable, or it's promoting the reaction in some interesting way. There's lots of different ways a catalyst can do this, but effectively it's lowering the activation of this reaction by helping out in some way. The image on the right shows a catalyst that maybe provides a different sort of mechanism that the reaction can occur so that it also has a lower activation energy. So maybe the key step in the mechanism for this first plot is unimolecular. And that's still true when you add a catalyst. It's also possible that the elementary step that is sort of the rate determining step in your reaction can sort of change in how it progresses. And so maybe it's still unimolecular, but it happens at a different energy, produces an intermediate, which is this position on this plot. So this is our intermediate, which we talked about in the last video. It's its own stable thing that can form, and maybe it forms a different product. And so catalysts speed up the reactions by lowering activation energy, either by affecting the way that the reaction's happening or making it so that it's more likely that particular mechanism will happen. But this is sort of what the catalyst is doing. And there are two common types of catalysts that we like to talk about. And so I'm not going to focus on this too much, but I want you to just know sort of some of the different ways that catalysts can help us do reactions, because most industrial systems use catalysts, a lot of biology uses catalysts. So catalyst is something that's just going to kind of keep coming up throughout any STEM courses you take. And it's something that's really important because a lot of reactions don't happen as fast as we would like. So we rely on using homogeneous and heterogeneous catalysis to do a lot of cool stuff. So homogeneous catalysts are catalysts that are in the same phase as the reactant. So if my reaction is a gas phase reaction, then my catalyst is a gas phase catalyst. If my reaction happens in liquid, it happens in my beaker on my desk, my catalyst is also a liquid. And like solid-solid catalysis, same phase is the most important thing if it's homogeneous. If it's heterogeneous, then the catalyst is in a different phase than the reactants. So a lot of times in heterogeneous catalysis, people mean there's some sort of solid that you pass a liquid or a gas over. And when you do that, different chemistry happens, or chemistry happens faster. And so that's often the case. You can also have liquid catalysts in solid systems or in gas systems. There's a lot of range in chemistry, but you'll most often see a heterogeneous catalyst that is solid interacting with chemistry in a different phase. And so I wanted to show you an example of homogeneous catalysis in the context of the reaction we talked about in the mechanism video. And so ozone degradation, or sort of depletion, can happen sort of by itself in the atmosphere. But if you also have things like nitrous oxide, then there's new mechanisms that ozone can be degraded by. And so instead of producing an oxygen by itself, it's possible that ozone can react with NO, sometimes called NOx, and it can do degradation via a different path that happens faster. And so this can be good or bad depending on where the ozone is and what we're trying to degrade. But ultimately what it does is it's providing this system a different mechanism where it can undergo the same net reaction faster. So the first thing is if I look at the net reaction here, I'll have the same net reaction. So if I cancel out NO with NO, NO2 with NO2, sorry for the weird line, oxygen and oxygen, I'm left with the same two O3s and the O2 and three O2s in my net reaction. And the only difference for these is that in this system, I've explicitly included this NO catalyst, which is there at the beginning of the reaction and present at the end of the reaction. And so I've crossed them out here because they don't affect the net reaction. They are just serving as catalysts. So if I wanted to write this as a catalyzed reaction to explain that it's happening faster, I should still write it as NO plus 2O3 goes to 3O2 plus NO. And so in this net reaction, my catalyst appears to not be consumed. What actually happens is this catalyst underwent chemical changes and then was recovered. And so oftentimes in homogeneous catalysts, this happens. It's also possible through this reaction or through other reactions that you have an O on one side and then on the next side. So both are possible as long as in the net reaction for a catalyst, it's there at the beginning and it's there at the end. It's recovered if it's consumed. And so that is more often the case when you look at heterogeneous catalysis. And so if you have a surface here that chemistry can happen on, then the surface does catalyze this reaction by attracting different species that are going to undergo a reaction and helping them interact with each other so that they more quickly perform the desired reaction. And in this system, never once does the nickel actually join with a different system. The nickel in all of the equations that one would write for the reactions happening or the elementary steps happening on this heterogeneous catalysis, in none of them is nickel transformed. And so in this heterogeneous catalytic system, the catalyst is never consumed. And it doesn't have to be recovered because it's never consumed. And so whether the catalyst is consumed and then replaced, or whether it isn't consumed and just helps lower the activation energy, both types of catalysts work by speeding up reactions and lowering the activation energies by potentially changing the mechanism for which the reactions happen, or by somehow stabilizing or helping achieve the transition states of particular mechanisms. And in different courses, and in this course, we're going to talk about maybe some different types of catalysts. But the major thing is to remember that they affect the activation energy and that they're present at the start of whatever net reaction you have and at the end of whatever net reaction you have. Even if maybe some stuff different happens on the in-between steps of a particular mechanism.